Hi guys, okay, so in this week's video, what we're going to be talking about are piecewise limits and limits at infinity. So this is nothing too new or complicated. We're going to be using the same sort of skills and techniques that we developed these last 2 weeks and apply them into just piecewise situations and piecewise functions. So kind of going back to week 1, the biggest piece that's important for when we're looking at piecewise functions and the limits is that our value from the left and the right, like the limit, they need to be the same for the limit to exist. So if this one, the limit as x approaches 0 from the left, needs to be the same as the limit as x approaches 0 from the right. Okay, so we'll just go ahead and get started on this. So first thing, again, we need to look at the limit from the left. So the limit as x approaches 0 from the left, remember that's how we denote left, that little like exponent up top is a negative sign. Now we need to make sure we pick the right function. So piecewise we're given 2, if not more, right? But so for these we're just given 2. And so the left, we're going to want any values that are smaller than 0, right? So we're going to actually use this function right here, this line. So we're just going to plug in x. So the limit as x approaches 0 from the left of x, right? We can just go ahead and substitute in 0 for x. That's going to equal 0. Okay? Now we need to do the same thing for the right. So the limit as x approaches 0 from the right. So the right is going to have any numbers that are bigger than 0, right? So we're going to use this x squared. When we substitute that in, we're going to get 0 squared. So our limit equals 0. And so since our left limit and our right limit are the same, this tells us that the limit as x approaches 0 of f of x equals 0. Okay. I think I talked about this in the first week. Those 3 little dots, they just mean therefore. Mathematicians are incredibly lazy, and so we've come up with a million different shorthand things or little abbreviations to use. So yeah, that's just all those 3 dots mean. So if you see me using them, that's what I'm doing. It's just kind of nicely summarizing, since this equals 0, since this equals 0, therefore our whole limit has to equal 0, right? Alright, on to the next one. So again, we want the limit as x approaches 1. We need to find the left and the right, so then we can make our conclusion about this limit. So we need to find the limit as x approaches 1 from the left. Okay, again, left, we're going to have values less than, think left less, right? So we're going to use this function, x squared plus 1. When we go ahead and substitute that 1 in, we're just going to get 1 squared plus 1. So our left-hand limit equals 2. Okay. Next up, we need to do the limit as we approach 1 from the right. Okay, so the right, we're going to have bigger numbers, x values that are larger than 1. So we need to use this function, the 2x. So when we substitute in, we get 2 times 1, so our limit equals 2. And since our left limit equals 2, and our right limit also equals 2, therefore, we know that the limit as x approaches 1 of f of x equals 2. Something really important, a lot of students might mess this up. This little negative, again, this only indicates if it's the left or the right, this exponent. So when you see this negative, don't think that you need to plug in a -1. Okay, you're still just going to plug in a 1. This negative or the positive, that's just telling us which side we're approaching that x value from if we were to be looking at a graph. Okay, so just make sure to be careful about that, because if you were to plug in -1, we would not be getting this right answer. Okay, next one, number 3. Same thing, we're going to do the left and the right. So the limit as x approaches 3 from the left less, right? We need to use this one, 2x plus 4. When we plug that in, we're going to get 2 times 3 plus 4. So 6 plus 4 is going to equal 10. Now we need to do the limit from the right. So the limit as x approaches 3 from the right, those x values are going to be larger than 3. Okay, so we need to use this function, the 3x minus 1. And when we substitute in, we get 3 times 3 minus 1. That's going to give us 9 minus 1, which equals 8. And so, unlike our other examples, we can see that since our left limit and our right limit aren't the same, that's going to tell us that the limit as x approaches 3 of f of x does not exist. Okay? So again, like that week 1 when we were looking at graphs, now we're just doing this algebraically. We did a lot of piecewise graphs week 1. Now, if you remember, I kept saying how we'll have algebraic ways to do these in a few weeks. This is them, right? So yeah, we're just kind of building on stuff that you guys have already been doing so far, and you guys have been doing really well with as well. So hopefully this is pretty straightforward. Alright, number 4, this is a little different than our last example because of how our function's defined. So instead of having x less than 2 and x greater than 2, where we clearly know the left and the right, this one's actually a little easier because what this is saying, this line right here, so f of x equals 5 when x equals 2. What that means is we can kind of rewrite that if we want as f of 2 equals 5. If you guys recall, from the first week, when we had this and we were looking at our graphs and we found our function values, this didn't matter for our limit, right? We didn't really care. This was just telling us what our function value was at a certain x value. But for our limits, what we care about is we want to approach our function, or our x value, from the left and the right. So that's what this x is not equal to 2 is going to give us. Okay, so it's saying when x is not equal to 2, so at any other point in the graph, when it's going, that's the function's going to be like actually graphed. So this would give us there'd be a hole at x equals 2, right? Because of this denominator, if we were to factor it. So that's why this needs to be defined, f of 2 equals 5. But so we don't have to worry about doing the left and the right since we're just going to use the same function. So we can just go ahead and find the limit as x approaches 2. Our f of x is going to be this. I'm actually going to go ahead and skip a step and just factor right from the beginning, right? Since we know, since we have a fraction, we're going to need to factor it. So this top is going to factor as x plus 2, x minus 2. Our denominator is going to stay the same as x minus 2. Okay. Since we have both of those x minus 2's, we can cross them off. So we're left with the limit as x approaches 2 of x plus 2. So now we can go ahead and substitute. We're just going to get 2 plus 2. So our limit equals 4. And like I said, since we didn't have to worry about the left and the right, since this covered both sides, that's it for this one. So we just have the limit as x approaches 2 of f of x equals 4. Alright, number 5 is written the same way as number 4, in that we have what this little bit's telling us. If we were to plug in that x value, that 5, into here, that's what our y value would be. This would give us our y value. But what we care about our limit. So we're just going to focus on this part right here where its x is not equal to 5. So we'll start with the limit as x approaches 5. Again, I'm going to go ahead and skip this instead of just rewriting this as I'm going to go ahead and factor right now. Our top is going to factor as x minus 5, x plus 4. Okay, our denominator is going to stay as x minus 5. So since we have both of those x minus 5's, we can cross them off. So we're going to be left with the limit as x approaches 5 of x plus 4. So now we just go ahead and substitute in. We get 5 plus 4, so then that's going to equal 9. So we have our limit as x approaches 5 of f of x equals 9. Okay, so although these you don't have to do the left and the right, you are typically going to get a fraction, so there is that added step of having to factor and cross things off and kind of clean up your entire expression. But yeah, so I'd say still equal amount of work between the two different types of piecewise functions you have. So going on to this last example, we're back with our inequality. So we're going to have to do our function from the left and then our limit from the left and the right. So we'll start with the left, the limit as x approaches 1 from the left. Again, left less. So we need to use this function, this x squared plus 7. Okay. So we go ahead and we substitute in, we get 1 squared plus 7, that's going to give us 8. Okay, now we need to do the right. So the limit as x approaches 1 from the right, again, we're going to need to use x values bigger than 1, so we need this function, the 3x. So when we substitute, we have 3 times 1. That's just going to equal 3. And so for this one, since we see that our left-hand limit and our right-hand limit are not equal, this tells us that the limit as x approaches 1 of f of x does not exist. Okay? So that's going to be it on piecewise limits. Again, shouldn't be too difficult. Worst case, if you did really want, you could always graph these when you're doing your math-based stuff. I personally feel that the algebra is easier and just quicker. But if you do want to use the graphs to check or anything like that, I think that would definitely be a good idea. Yeah. So next bit that we're going to talk about, we're going to go ahead and talk about limits at infinity. So this section is a little new. It'll look new, but you guys actually know this information. You just don't know you know it. Okay. So when we have limits as x approaches infinity, we just have these 3 rules that we're going to follow. Okay. These are actually, I know this was like a while back for you guys, but these are exactly the same as the asymptote rules that you guys talked about a few units back. So I know it's been a while. Gotta like dust off those cobwebs from that information, but they are the exact same rules. So this will be actually really helpful. Yeah, so our first one is, our rule is that if the degree of the numerator is less than the degree of the denominator, so top less than bottom, right, our limit's going to equal 0. Okay, so if we look right here, we can see the top is less than the bottom, so that limit's going to equal 0. Same thing, this is our same function, we're just approaching negative infinity. You can also just use the graph, like I mentioned previously, if you want to check. I would plug these into Desmos, and you can see, as x goes to the right, our function is going to approach infinity, or approach 0, but never actually touch it. Same thing with the left. If as x is going towards negative infinity, it's going to get super close to 0, but not actually touch it. Okay, so if our degree of our top is less than the degree of the bottom, our limit equals 0. Now to the second one, if the degree of the numerator is greater than the degree of the denominator, so if the top is greater than the bottom, our limit does not exist. Okay, so again, these are the same rules as our asymptotes. So if we were to look at this one, since we have an x cubed up top and just an x to the first down here, this means our limit does not exist. And then the same thing right here, because it's the same function. So when we look at the graph, if we look, as x is going towards positive infinity, our function's not stopping, right? Like, it's going to go on and on and on and on. Same thing this way, as x goes towards negative infinity. We're going to go on and on and on and on and on, nothing stopping. So then our last rule is going to be when our degrees are equal. So if the top equals the bottom, right, then we need to do leading coefficient divided by leading coefficient. So this one, right in front of this x squared, there's actually a little 1, right? Whenever you don't see it, there's a 1 in front. So they're both x squareds, so our limit is going to be 3 over 1, which is just equal to 3. Same thing down here, our limit's going to equal 3. And if you look at the graph, as you go towards positive infinity and negative infinity, it's kind of hard to see in the video, but our function does kind of trail off right there when y equals 3. So it gets super close to that value, but never actually equals it. Okay. So now just a few examples. The way I like to do it, very visual. I like to actually just like circle. Right, I like to circle our highest degrees. So this one, I just circle it. Alright, we have an x squared on top and an x on the bottom. So our top is greater. Okay, when our top is greater, that means our limit does not exist. Okay. We'll go over to this side. This next one, we're looking at circle them. Circle the highest degrees. This is an x to the first up top and an x squared in the bottom. So since our denominator is bigger, that means our limit is going to equal 0. Right? Number 3, we have x to the firsts on both the top and bottom. So our limit is just going to be leading coefficient over leading coefficient. Lucky for us, both of these leading coefficients are just 1. Alright, so that's just going to equal 1. This one is a little funky, okay? I'm sure the square root would throw a lot of people. The way I like to look at these, for our limits, we're only concerned with our highest degree, right? So our highest degree in the top right now would be this 4x squared, but that's under the square root. So we're just going to kind of ignore this plus 1. And if you're to consider 4x squared, all of that under the square root, over x, right, because that's what we have in our denominator. 4 is a perfect square, so is x squared. So we can actually rewrite that as just 2x over x, right? Because square root of 4 is 2, the square root of x squared is x. So now we'd still have plus whatever the remainder is, right? But again, we're only focused on our leading terms. So now these have the same degree, okay? So it's going to be leading coefficient divided by leading coefficient. So we have a 2 up top and a 1 on the bottom. So our limit is going to equal 2. Okay? I know this is probably a little weird, but again, you're only focused on your highest degree, so you can, as bad as it probably sounds and like against everything y'all have been taught, you can ignore the rest of the terms. This is the only instance in which you can do that, okay? So don't go like running around thinking you can do that for all your future problems. No, just when you have the sort of square root situation, you're only focused on your highest degree. Okay? Number 5. Go ahead and circle that. We have the highest degree on the top is going to be a 3, and our denominator is a 2. So since our top is greater, that tells us that the limit does not exist. Okay. Number 6, and we'll do both of these at the same time since they're the same kind of question, right? These are actually really interesting. So although there's not a fraction, you can kind of write it as 1, right? So you can write it as 1. 1 is the same thing as x to the 0, okay? Or anything to the 0 power, right? So if we really wanted to examine exponents, obviously our top is greater with an x cubed up top, so this one does not exist. Same thing down here for number 8, since we just have this quartic. There's no fraction. This limit does not exist. So yeah, whenever you have a function, it's just one line, your limit's not going to exist, because although there isn't a fraction, clearly your degree on the top is going to have to be greater than the degree on the bottom. If the degree on the bottom was greater, or even equal, there'd be a fraction, there'd be a denominator present. But since it's just one line, obviously your top is going to be bigger, therefore the limit does not exist. Okay? Going into the last few, number 7, we're going to go ahead and circle. These both have 2's as their exponents, right? So we're going to do leading coefficient over leading coefficient. This negative can either go with the 2 or with the little 1 in front of that x. Totally your preference. I prefer to just put any negatives if they're right outside. I just like to put them up front. I think that's the clearest. So we have negative 2 over 1, which is the same thing as just negative 2. So that's our limit for that one. Number 9 is kind of similar to 6 and 8 in the sense that you only have an x on one part. So for this one, again, there's no x on the top. If you really wanted, you could multiply this by an x to the 0, since that's the same thing as 1, and you could examine it that way, or with the same logic that we used in 6 and 8, since there is absolutely no x on the top, we know that our degree on the bottom is going to have to be greater, right? So therefore that limit is going to equal 0. Okay. And then this last one is actually kind of cool. I'm not going to talk about it too much. It's similar to number 4. It's the same function as number 4. It's just the limit is approaching, in number 4 it approached positive infinity. In the bottom it's approaching negative infinity. So if you were to look at this on Desmos, it looks kind of funky. And I think the answer is actually going to be negative 2, the limit. And that's because when you take the square root, you get a plus or minus. But initially when we were focused on going towards positive infinity, it was obviously going to be a positive 2. Since it's negative infinity, it's going to be a negative 2. Don't worry about this question. I don't even know if a question like 4 will be on math space, but nothing like this with the negative infinity where you would need to see the graph. is going to be on math space or the assessment or anything like that. So don't worry if this stuff, the square root ones were a little confusing. Don't worry. I promise the ones on math space and stuff are going to be really straightforward, and just kind of focus on like these concepts more without the square roots. So yeah, that is it for week 3's video. If you have any questions, let me know.